professor in electrical engineering here and also the chair of the electrical engineering department. And she got her PhD from MIT, actually, with Herman House and Eric Ippen group, a very well-known group there, and did some nice work on quantum optics. And also did a sabbatical at IBM, and really from there got into thinking about photonics, photonic networking for data centers and in computer networks. It was one of the first, I think, to really get into that area, and has been a pioneer at thinking about photonics in this way, and even driving it all the way down to using integrated photonics and thinking about putting it on chip. And she's done a lot of important work in that area. And today she's going to tell us about some of the work that she's doing on silicon photonic interconnection networks and high-performance data centers.
Great. All right. Thanks so much, Dan, for this kind introduction. And thank you to the folks that joined this webinar. Just a note: if you have any questions, I think you can type them in, and I can definitely try to discuss them at the end of the presentation. And so if you think of something along the way, you can just type it in. And also, very happy to follow up. This is part of our CIAN ERC lecture series. So very happy to follow up with any of our industry members and collaborators. So this is the first slide. I just wanted to mention that we are actually celebrating the 150th anniversary of the Columbia School of Engineering. And this is a really important year for us. We had a big gala. This is just supposed to show that even within the hustle and bustle of New York City, Columbia is actually on a beautiful campus that you see on the bottom. Sometimes not expected by people that come to visit. So my seminar today is going to be about thinking about how to design scalable computing systems with various forms of optically enabled data movement. And besides the strong support from the NSF and CIAN, this work has broad coverage from DARPA and DOD, as well as Department of Energy and other industry sponsors. So I'm going to give kind of an overview of several different projects really integrated into this discussion. So what's been happening in computation really over almost the last decade, since about the mid-2000s, has been a very important migration from what we've been seeing in microprocessors, which is the microprocessors going faster and faster with faster clock cycles. Those of you that perhaps are a little bit on my generation, a little bit on the older side, and the students, you remember that we used to get a new PC every couple of years, and you used to have the new Pentium chip in it, and it would go like twice as fast or 3 times as fast. So that has basically stopped as of the mid-2000s. And what's been happening is, because of the power dissipation associated with increasing frequency of the microprocessor, we decided that the computing industry basically had come to the conclusion that continuing the scaling of the frequency or the speed of the microprocessor was unsustainable because of the power dissipation, associated heat of increasing those frequencies. And so it was a very big paradigm shift to go from a single uniprocessor to multiprocessor or multi-core architectures. And this is really a major paradigm change in computation that started about almost a decade ago. And it is a revolutionary change in computing architectures as we've had. And what that did was, instead of essentially having computation continue to be dependent on how many flops you can have on a single chip, the value of computation or the performance of the system started to depend much more on how efficiently you can communicate between these multiple cores or multiple processors that now all existed in the same place. So we've seen a vast increase in essentially the parallelism of these systems. And that's what I mean in the slide, is that we've really transitioned from a computation-bound systems to communication-bound systems. And it's very important to kind of understand this fundamental shift in essentially all platforms of computation, from handheld systems that you see on the bottom to embedded systems and to very large-scale data centers and supercomputers. And of course, this is where optics enters, because the thought is that communication is a function that is very well handled by the optical domain. And one of the reasons that optics is being considered in these highly parallel systems is that moving the data between these growing vast parallel resources that we now see in all platforms of computation has very substantial energy costs associated with that. And what you see on this slide is, in picojoules, how much energy does it take to move a double precision floating point operation, the equivalent bits associated with a double precision flop. So on the very left side, you see the current and the projection for a few years from now, how many picojoules it takes to do that one computation. And then as you go further and further to the right, you're moving through larger distances of the system. First, you're just moving to a register, which is a very, very short distance within the same chip. And of course, that's a very low amount of energy. But then as you really start to communicate across the chip, and especially when you start to communicate to off-chip DRAM, we see almost a cliff in terms of the amount of energy that now takes to move that same amount of data. So the message here is that the amount of energy that you spend on computation versus the amount of energy that you spend on moving that same amount of data that you use in your computation is much, much higher. Moving that data is much higher than the computation. And all of computing architecture is basically designed with this in mind, so that I'm not going to be moving data unless I absolutely have to, because the cost and energy is so high. And many systems today, especially as they become much more parallel and with many, many more cores, and you can imagine the multiplicity of that, are really focusing on designing applications and algorithms and everything that they could possibly do to keep the computation local. Because moving that data especially to off-chip memory, is just so extraordinarily expensive. And as the bandwidth that you need to move, and as the computation grows, the energy growth associated with moving that data to across your system is really astronomical. In many cases, really impossible to do. So this is probably the most challenging problem in computation today. How do you scale applications while keeping the algorithm local? And just to kind of give you a little hint of this problem, there are many problems that just cannot scale unless you are able to move the data. A very good example of that is like doing a computational FFT, where you have to move data across the entire system in order to solve that kind of problem. It cannot be divided up into small bits and done locally as easily as other computations. Okay, so photonics enters into the picture. We all know that optics provides an amazing communication medium. We know that from fiber optics and so forth. And looking at it from the computing system perspective, the way we think about photonics is that it moves data in a very different way than we currently move data with electronic networks. In electronic networks, which you see on the right side, we have to essentially generate the bits. We always have to do that. But then we have to receive the bits after a very short propagation distance, could be millimeters on a chip. And we have to then regenerate those bits and retransmit them. The reason for that is basically the losses associated with moving these electrical bits. Secondly, each wire can only carry essentially one signal. In other words, we cannot put in multiple signals into one wire like we can with WDM. So the way that the electronic communication has to happen is all these wires are coming in parallel. Every single bit from every single wire has to be regenerated, perhaps routed into the network, and then retransmitted. Buffered, received, and retransmitted. In the optical domain, we have kind of the opposite situation where we can put all the photons together. The photons obviously can have very high bandwidth densities, and we can send a very large number of wavelengths all in essentially the same quote-unquote wire or photonic waveguide or photonic cable. And so the bandwidth density possible with optics is one very essential difference and also one very, very important advantage that we have. The second important design aspect is the routing aspect. As I mentioned, in the electrical domain, we have to receive every single bit individually. We have to then route it, buffer it, route it, and retransmit it. In the optical domain, we have the ability, don't always have to use it, but we have the ability of essentially routing all the wavelengths together, very high bandwidth, because we can build the equivalent of an optical switch or an optical mirror that can be very broadband, can take all the wavelengths together and then switch their direction into a network. And this wavelength parallelism of the routing or the switching, which can happen with very fast circuit switching, is another very different way of data movement that we have in optics versus electronics. Again, this is very simple stuff that we all know about photonics, but it's just the reason I'm going into it is that it's just very important to understand how things are done today in electronic networks, and these are very fundamental difference in terms of optical data movement. That if we want to design optical networks within computing systems, we really have to take into consideration, almost redesign the architecture in a way that takes advantage of these very specific optical communication characteristics. If we do all that extremely well, what we end up getting is this so-called distance independence of the bandwidth density. So whereas I showed you in the previous diagram the energy consumption associated with moving off the chip, how it grows by an order or two, maybe even 3 orders of magnitude. In the optical domain, once I transmit those bits, once I generate those bits, I can essentially move them across my system without having to regenerate them, for the most part, because the distances that I'm going across the system are relatively short compared to fiber optic communication networks. Now, yes, there will be optical losses, and yes, at some point there will be some amplification that's needed, but that can be done over the broadband of the wavelengths. So the promise is that I can have off-chip bandwidth that's equivalent to the on-chip bandwidth for nearly the same power dissipation. This is a statement that is completely unheard of in computing systems. Like I said earlier, all computer systems are created with these hierarchical architectures because of these cliffs that you get in the power dissipation as you go off the chip. And you can break that with the correct design of a photonic system. And another way to essentially show the same message is that's related to the bandwidth density is to look at the pin count. What you see here is a plot that we generated a couple of years ago, where we designed a hypothetical 10 teraflop system imagine a board level or embedded level system that is able to generate 10 teraflops. And what we wanted to do was see, with the best of class systems, what would it take to have 10 terabytes per second of communication bandwidth to memory, to external off-chip memory from the 10 terabytes. This is just using nothing more than a rule of thumb that says to have a balanced system, you want to have 1 byte of communication bandwidth per flop of computation. Doesn't mean that's not a physical fundamental rule, it's just a rule of thumb. And when you are able to do that, you get very efficient usage of your computation. As a side note, today's high-performance systems are lucky if they get 0.01 in terms of the balance between the communication, the memory communication bandwidth, and the computation. That's how steep that cliff is in terms of going off chip. So we tried to design the electronic system, and what you see in the with the green, okay, go back. What you see with the green line and the triangles on the right side is essentially the number of pins, assuming very aggressive numbers for the electronic wires, the number of pins that would be required to make that kind of a system, that kind of balanced system. And those numbers of pins start at about 10,000 and go up from there, which is, imagine a chip with 10,000, 20,000, 50,000 pins. That's impossible, almost impossible to do. Right? You know, you're not going to have anything left for power and other issues. But if you design the same system using optical, quote-unquote, optical wires, because of the bandwidth density, you're able to have that orange line that you see on the bottom with hundreds of IOs. So what the message from this slide is not that optics is more, not just that optics has more bandwidth density than electronics. Yes, we all know that, because you can put in lots of wavelengths into the same wire. The message here is that you can build systems with optical wires that are impossible to build with electronic wires. That's really the powerful message here. Secondly, what you see here are the bars, which indicate the power dissipation associated with all those wires. And as expected, the power dissipation of the optics, which is shown in the orange bars, is substantially less than the power dissipation associated with building all of those electronic IOs. And again, that makes it possible to build these balanced systems. What does a balanced system mean? It means I can actually have a system with enough communication efficiency among all these parallel resources that I mentioned earlier, with all the multiple cores, and grow them into large-scale systems, and actually solve real problems with fast execution times. At the end of the day, you know, the reason that we build computer systems is not just that we have beautiful computer systems, it's to actually solve real problems, real applications. And so this is about a capability, not just the concept of I can go faster, I can have more bandwidth density, I can have less power. This is about getting a capability of computation that is impossible to do with current electronic systems. So the silicon photonics comes into the picture pretty much around the same time as this multi-core revolution or paradigm shift that was happening in computing. So around the mid-2000s, we're able to fabricate photonics in the silicon platforms, SOI, primarily because of the 90 nanometer feature size with enough low loss that the waveguides are maybe some fraction of a dB per centimeter, if things are very, very good. And so we can actually start to make optics directly within the silicon platform that has low enough losses to make meaningful devices, waveguides. We can even make the ring modulators that we couldn't make before because of the low losses. We can have enough of an electro-optic effect by having rings with very high Qs. So it's really, you know, it's a really beautiful story where these two challenges and technologies came together. On the one hand, completely separate community of multi-core processors, computer architectures, are starting to get this increasingly important challenge of the parallelism and the power associated with communications. And on the other side, we make a breakthrough in photonics where we can actually put photonics on chip in silicon, using all that silicon infrastructure that exists for semiconductors. And so, and many of you are familiar with some of these achievements. This is an example, I believe, from IBM from a few years ago, just to show the kind of bandwidth density that's possible. 2 terabits per second over 20 micron. That kind of bandwidth density is, like I said earlier, is an impossibility with an electronic I/O. So we've come a really long way in silicon photonics. And the slide really indicates that we have essentially all the necessary building blocks. We have created modulations, whether they're ring modulators or Mach-Zehnder modulators, essentially active devices in the silicon platform. We have low loss optical waveguides, so we can go meaningful distances on the chip, centimeters on the chip, and then we can connect off the chip with immense bandwidth densities to go into optical fibers or other, polymer or other kinds of interconnects. And we have the ability to take advantage of this dense WDM, again, primarily through the ring resonator structure, where we can have extremely aggressive WDM platform. And I'll show you some real designs that we've done that show you the possibilities of these interconnects. And lastly, we're able to make the equivalent of these broadband switches. What I show here is one of the routers that we made together with Cornell, which is a 4x4 non-blocking router, but using rings. But there are many other switch fabrics possibilities that have been shown. In fact, I would say that's probably the most important next challenge for silicon photonics is to make a larger, high-radix switch fabric that is low enough loss and has nanosecond time scale. We're not quite there yet. So this is the example, the canonical example, at least that we use for the modulator device. This is the active ring. As many of you, I imagine, are familiar, you can apply very small current or voltage, and essentially what you're modulating is the transmission spectrum of the ring resonator, and apply like an on-off key modulator. And there are many variations on this design now. I think the essential points here are that it can be done with very, very low energies. I mean, record energies have been shown, for example, femtosecond, the famous resonator, also from that Mike Watts showed with very, very low power on femtosecond, femtojoules per bit, as well as the some of the very high-speed ring resonator modulators that we're using, also in collaboration with Cornell, and as you'll see later, also that we've been working with the OPSIS platform and our collaboration with Hochberg. Okay, why is this important? Why is the ring important? Essentially, it's that you can transmit very dense. You can actually take advantage of this. What I showed a little bit in one of the first slides of how the optical transmission works. That you can take advantage of the bandwidth density through WDM. And so by stringing together a bunch of these rings that would overlap with the different resonances corresponding to the size of the ring to correspond to different wavelengths, you can stack up very dense WDM transmission. And as with any design, any engineering design, there are all kinds of constraints and engineering trade-offs that happen. But essentially, at this point in time, several companies have actually demonstrated highly functional WDM transmission using this kind of technology. So one question that comes up, which is a result of some work that we did a couple of years ago. This was at the time when a lot of these silicon photonic devices were starting to really come online as individual devices, and the computing community were starting to take notice as the potential of using these devices for high-performance interconnects. And so the question came up as, let's really dig in. That means both the computing community and the optics community. Let's dig in and really figure out, where we can take this technology for real manufacturable, real components that can go into systems in a relatively near term, meaning 3-5 years. And to do that, we wanted to think about the design that encompasses the entire system. So not just a single ring, but really takes into account, the engineering trade-offs of making a high-density array that takes into account, the external lasers and receivers and electronic drivers and so forth. And so we worked together with, this was actually a workshop that I was one of the co-organizers. It was sponsored by the DoD and the DOE, and included companies, some of the leading companies in this area, just to mention a few, the IBM and Intel, HP was there. We worked, and Sandia Labs was involved as well as other government labs. So we worked, our task was to work together with some collaborators from Intel on designing this highly dense WDM micro-ring based link. And so you see here the picture of that. And the question was, what is the real optical losses that we can expect in this design? What are the trade-offs? And what is the power dissipation? What is the joules per bit that can be expected in this kind of link design? And so we went into some pretty detailed analysis. Just to give you the highlights, when you design a link, of course, there's going to be some higher limit on how much optical power you can put into that link. It's going to be limited perhaps by nonlinear effects and other factors. And on the bottom side, there's going to be a limit in terms of your receiver sensitivity. What is the lowest number of photons or the lowest power that you can actually capture while still maintain an error-free transmission links? And as the bit rate goes up, that optical power budget starts to close on you, and that, of course, is a very important trade-off in the design. And so what we did was we actually had, there's a paper in IEEE Micro, if anyone is interested in further details, 2013, where all these details are laid out. But basically, what we did was we had two design points, one at 12.5 or really 10 gigabit per second, and another at a faster speed, 25 gigabit per second per channel. And looking at these two designs, of course, one of the expected results is that the power per channel is going to be proportional, inversely proportional with the channel spacing. So as you have larger spacing, you can put in less power per channel. And in this particular design, we were able to show that just in terms of bandwidth density, you could get to almost 2 terabits per second in a single optical waveguide, single silicon photonic optical waveguide. So this includes all of the parameters associated with the optical losses. Really, every single component in the optical path is taken into account in this design. And if you go to a more dense design with a lower bit rate per channel, because when you have a lower bit rate, you can put the channels closer together because they have less overlap. You can squeeze out a slightly larger bandwidth density. That also has to do with the fact that at the lower speeds, your receiver is more efficient as well, has a better sensitivity. The other aspect that we looked at besides the optical power budget was the power efficiency. And again, even though these numbers may seem pretty simple, each one of them has behind them pretty extensive analysis of the circuitry, the thermal stabilization that's required, and all the assumptions into making that complete link design. So we accounted for every single component along the link in terms of the energy dissipation. This is not including amplifiers for these two different design points. And what we find is that, as expected probably, the biggest culprit to the entire power budget is actually the laser source. So unfortunately, the laser sources that are, at least in our design, the assumption was that the laser source is sitting off chip. So this was a standard telecom WDM type of laser source. And these laser sources were never designed to be, particularly energy efficient. They were designed for telecom systems, for not necessarily using a large number of them and so forth. And so the wall plug efficiency of these lasers, commercial ones today, is probably like about 1%, perhaps a little bit better. That includes all the thermal stabilization and all the tech and all the stuff. And so if we use off-the-shelf telecom lasers, we're basically hosed, because it kills the entire link power budget that you would expect to get from a photonic system. But if we just increase the efficiency from 1% to 10%, which is not fundamentally impossible, actually very, very, very possible, perhaps by using multi-wavelength sources, perhaps by looking at the possibility of on-chip lasers, hybrid integration, and so forth, if you can just go up to 10%, then you're back to having an extremely efficient and extremely high bandwidth density optical links. So this is an absolute must in terms of actually getting to any real systems that use silicon photonic links. This is actually a slide that I like to use when I speak to more of the high-performance computing audience, because they always say, well, these photonics people, they've been talking to us about optical interconnects for so long, but all we see is these research papers. And yeah, we still have a lot of research papers, but I wanted to show them that we've really advanced towards, there's just a multitude now, this is already an old slide, now there's a multitude of companies that are really making silicon photonic devices and components and interconnect technologies in the commercial world, and it's becoming more and more going forward, where some of the bigger, even computing companies are having parts of the companies that are dedicated to this. So this is becoming real in terms of both the fabrication infrastructure, the ecosystem, so forth. We're not there yet. We're semiconductor are by any far stretch, but we've definitely come a long way. So in our lab here at Columbia, we've been working over the last few years with, as I mentioned earlier, with Hodgeberg, who led the OPSIS that is no longer running, but we're still continuing the collaboration. But this is just one example of one, in my opinion, extraordinary example of when you really start to get the massive photonic integration, you are actually able to make chips that deliver the kind of performance that it's really impossible to do with a single researcher in a single lab, in a single kind of academic lab. And this is a single chip, single device on the chip that is actually 8 channels at 40 gigabit per second for 320 gigabit per second WDM transmitter on a silicon chip. I mean, that is, a few years ago, that was just an impossibility to think about that. And imagine doing that with a telecom system, with all the lasers and the lithium niobate modulators and the receivers and all of that. So having this kind of system on a chip is a huge achievement. This is an example from already a year ago, and I'll show you that it's even better than that. So the vision is to really take the silicon photonic components, the links, the modulators, the highly dense WDM, and now really think about how do you actually design the network in a way that can move the data within the system so that ultimately you're not just getting great photonics inside computer systems, but you're actually getting applications running on your computing system that are running much more efficiently, much faster, solving problems that were never possible to solve before. That's really, I think it's important to keep in mind that's the goal of the technology. Sorry, this is just a shameless advertising for my own book on designing those networks. So I encourage you to look inside. But this is really to set up the fact that one of our major efforts here is on the design side of it, design, modeling, and simulation side. Because unlike the semiconductor, the silicon industry, we don't have that ecosystem. If a computer architect comes and says, okay, I want to design a computer system based on silicon photonic networks, where's the CAD? Where's the simulation environment? Where is it? Does not exist. I know we have different kinds of optical software and things like that for designing devices and waveguides, but there isn't that software infrastructure that connects the physical layer that we know in photonics to the network layer and ultimately to the application layer. So what do I design? So the only thing that really exists today is, people from the computer architecture, they come and they say, well, I'm going to design what I know, which is I'm going to make an electronic network, an electronic switch, and maybe I'll rip out the electronic wires and put in optical wires. All right, well, that's nice. And, those optical cables, active optical cables, sort of get you to in some ways that you're able to connect longer racks to each other, in your high-performance computing system or data center. You're able to connect them with higher bandwidth, maybe slightly lower energy. They're still very costly compared to electronics, but that's sort of where you're at. But you're not really ripping the big benefits of photonics within the network, because you're not actually using the optical switching. You're not actually moving that multiple WDM capabilities that's available to you. And the design of optical networks within computing systems is going to have to be completely different than mimicking an existing electronic architecture, because optics just doesn't move the same way that the electrons do. So that's the reason that we've developed and are developing what we call this PhenixSim suite, which includes, at the lower layer, it includes a very accurate, or as accurate as needed, description of the physical layer. So we have a description of all these silicon photonic components that's captured. And then it connects that to a network design layer, and ultimately a system layer where you can actually examine the efficiency of running an application on top of that. And you have, by using this kind of software system, you're able to then do what we are aiming to do, which is a holistic design of the opportunities for mapping parallel applications, the kind of applications that are really hard to run on these massively parallel systems without communication. So mapping them onto an optically interconnected system and using the communication in the most efficient way that's available to you with the optical switching and the optical interconnect. And so this is just a very simple visual of the kind of design process that can happen. For example, if I change the architecture of the optical interconnect, that will change. You see in the green the amount of time that the processors, my computation resources, are actually doing real work. In the red zone, what you see is a very visual indication of the computation resources sitting there twirling their thumbs, just sitting idle, right? So this is a waste of energy. Red means a waste of energy. You're just wasting computational resources sitting around. And green is when you're really making efficient use of your system. And that's actually another very important, maybe an equally important aspect to think about in system design. So we may have all heard a lot of discussion in our community about optics in data centers, and the fact that by, the data, we all know that the data movement in data centers is one component of the power dissipation, one component of the power bill, which is very important. And okay, so we replace the electronic wires with optical wires, and maybe that's going to cost less energy, maybe. But the other big part of the energy consumption is actually, computational resources sitting there and not actually doing work. So you're running imagine you're running an application, but your system is only 1-2% efficient. And so you're wasting that other 90% of power just sitting around. And so the energy savings go beyond just replacing the wires. It actually goes by re-architecting the system. You're able to make the entire thing much more efficient. And the factor of power savings that you can ultimately get is much higher than just replacing that component of the interconnect with optics. This is some more examples of the code design. This is getting into a little bit more of the application and so forth. And I'll kind of flip through that because without going into too much details. What I want to show you is that in addition to these simulations, it's also, now we have to go back in the lab and actually put it all together. And so the other really exciting aspect that we're working on is taking the silicon photonic components, which are now really subsystems. They're no longer just a single ring resonator. They're no longer just a single switch and so on, that somebody writes a nice research paper on. They're actually chips that can be packaged and put into real systems. And the platform that we're using to integrate all of that into a system test bed is the FPGA. And what that gives us is an ability to control all the silicon photonic components so that they're stable, thermally stable, and also inject software programmability into the optical physical layer. And so we're actually, along these lines, one of the directions that we're focusing on is some joint work with Micron Technology as well as other partners. Micron is one of the high-performance, one of the largest memory manufacturers, maybe the largest in the U.S. for sure. And they have high-performance memory called the HMC, Hybrid Memory Cube. And this is a new memory architecture that came on just within the last year, for 2 years at the most, that is extremely high bandwidth. The current generation of HMCs has an I/O bandwidth of 320 gigabytes. That's 2.56 terabits per second. This is per chip. And so imagine creating an electronic interconnect that's going to connect up processors with this high-performance memory. It would be really hard to build, scale up this kind of system electronically. And so this is a really fantastic example of using optical interconnects, so especially silicon photonic interconnects, to connect up a scalable high-performance memory system. So this is the direction that we are focusing here. This is just a picture of the Micron HMC. As I mentioned, 2.56 terabits per second. It also has lower energy usage per bit than previous memory DRAM, more conventional DRAM designs. And so last year, this is without any optics. So last year, this is just to highlight the challenges that exist today in these systems on the I/O bandwidth. Last year at the biggest conference for computing, for high-performance computing called supercomputing, SC, Micron as well as other partners had a demo, and it was a board that had one of these HMCs on it. And it was the previous generation, so it was 1.28, not 2.56 terabits per second. And they wanted to show how to connect to it using FPGAs. And so they actually had 4 FPGAs, Stratix 5s, connected to it and running data back and forth from the FPGAs to the high-performance memory. And it took 4 FPGAs to connect up enough data to the high-performance memory to fill up that 1.28 terabits per second. You can see that it was 16 bidirectional 10 gigabit per second line, so very, very high speed, as best as they could. And then what happens is when they went off the board, they had to connect to a PCIe switch, and you can see the amazing drop in bandwidth as soon as you get off this board, right? You go from 1.28 terabits to 64 gigabits, and then even further down to 32 gigabits per second. I mean, this is how much is lost from the interconnect, and they couldn't do it because you can't transmit 1.28 terabits on any kind of distance electronically, at least with any kind of reasonable power dissipation. So I'm going to skip this part. Oh. Okay. And so this is essentially what we're doing. Exactly where that drop-off happens between the 1.28 and the 64 gigabits, we're putting the silicon photonics I/O. And so there, it's on the chip, it's connected to the FPGA in a controllable fashion, and then you can connect also to an optical switch. We're actually higher than the 1.28 now, we're working with the 2.56, but basically using these silicon photonic very high-speed I/O devices to make those connections, and then be able to connect to an optical switch platform. And I had just the slides reversed. So once we built that, so this would be one platform with the FPGAs and the high-performance memory, as well as FPGAs that have some computation on them. And the idea is to show that you can now actually make, through the optical network, through a switch fabric, you can actually make software-controlled, software-driven communications at extremely high bandwidth. And the concept that you can actually do this in the lab is very exciting. And the only reason that we're able to do this is that the photonics has come to a point where we can make chips that have transitioned from just being a single device in a research lab to chips that can work in a programmable, fashion, and can actually work in a repeatable fashion in this kind of system environment. So now we can actually physically test out some of the architectural designs and even some of the computation of application mapping and even programming models, so forth, right in this physical hardware system. So hopefully, so thanks again for those of you that did not go to sleep quite yet. Appreciate that. So I'll just kind of quickly summarize. If you did fall asleep or were doing your email, just take away one message. That when you design optical interconnects into photonic systems, into computing systems, it is not a wire-for-wire replacement. It really takes the entire redesign, re-architecting of the interconnection network. And the photonic switching, the ability to actually have a transparent path, is the key to giving you the performance gains, the capabilities that are possible beyond just a slightly longer reach that you might get with an active optical cable. So to really kind of break that dam that we have, that wall that we've had in the energy and the bandwidth and so forth, it can be thought of in very many different ways, really requires an end-to-end redesign of the system. You really need to take that leap. And we're at the cusp of being able to take that leap because of the hardware that's been coming online from the photonics community. So with that, I really appreciate the audience staying online. I know you're mute, so you can hold back all the applause, right? And so let me see if there's any questions. Is there a way to?
Yeah. So thanks, Karen. So if we have any questions, just you can put them on the chat question box there. Do we have any questions in the room here locally?
It's fine. I mean, I'm available for questions if anyone has want to send me an email or anything like that. That's oh, that's good. Trin wrote applause. That's good. Okay. Thank you, Trin. Appreciate that.
So Karen, let me ask you a question.
Sure.
Thermal issues with the photonics in there. So early on, that was a big issue with the micro rings and so forth. To what extent have we solved that problem, and what are people doing now in terms of, so for these energy calculations, is the thermal management included in that? Have we made things athermal?
Yeah, so all the calculations I showed include the full thermal control as well, under various assumptions. And I mean, the way that we handle it, I mean, it's basically an engineering problem that's completely solvable. So what we do is we've developed this automated ways of ensuring that all the components are wavelength stabilized. So we go with an active stabilization. We have various techniques of doing that, and with very low energy. So it just actively stabilized in our system test bed. It's done via the FPGA. That's 100% doable, and it's scalable because it's in the chip. There's you can do it by tapping off a little bit of light. You can do it many different ways. Very simple circuitry that's done. The other way to do it is to go with athermal design of some of these components, and that's good. That works too. And then the thermal load that you need to add, or you can actually design it to be stable over some range is fine. It is honestly not. It's definitely not the very large problem. I mean, I wouldn't say it's not an issue. It's always an engineering issue. It has to be addressed and solved. But it's, we're able to build systems, and then they run and they're stabilized over a reasonable window of temperature. So you can do it that way, or you can have a passive athermal design as well. The biggest problem, I think, I think this, if I were advising on like what to really dig into, there are two things. One is the lasers. So multi-wavelength, as low a wall plug energy efficient lasers as possible, possibly on the chip, and that connects also to on-chip amplifiers. That's really one of the really important challenges. And then the second is a very large, the largest possible high radix switch fabric. And the two kind of go together because a large fabric would probably have amplifiers in it, energy efficient amplifiers in it. So that those are really kind of the some of the exciting and doable high advanced technology challenges that will come online. So thank you, Dan, for the questions.
Other questions? Anyone on the bridge? Type in your question.
Okay.
All right. Well, that will thank Karen again, and thanks everyone.
Great. Thank you so much.
Yeah.
I guess we can take this up.